Hi, everybody. Over the last couple of weeks, we've been talking about stoichiometry, and throughout this whole semester, we've been talking about chemical reactions and the signs of them and how to predict the products. And with stoichiometry, we've added a math component to that. We've started talking about how we can predict how much of a product we will make. This week, we're going to take it a little bit farther, and we're going to talk about what really happens during the lab. Now, I wish that we could be in the lab doing experiments so that you could see this for yourself, but all of the experiments that we've done this year have had this principle applied to them. We just haven't necessarily put the vocabulary to it yet. So the topic for today's video is percent yield. Percent yield is basically what it sounds like. It's a percentage of how much product we yield. The key fact here is that when we do chemical reactions, we never make as much of the product as we think we will. We learned how to do stoichiometry and to predict how much of a product we will make, but we will never make as much as the math says. And that's because there's a lot of error in the lab. Some equipment has limitations. For example, some of the balances that we've used this year only record numbers to the tenths place. But if they could record numbers to the thousandths place, we would have much more precise data to work with. So there are limitations in equipment. There are environmental conditions such as the temperature of the room, the pressure in the room. Honestly, sometimes that it's raining affects reactions that we see in the classroom, and that's because it changes the barometric pressure. Then there are also technical mistakes in the lab. So anytime that you've ever accidentally knocked over something or maybe not filled up a pipette completely, those technical mistakes, right? When you get distracted by Cody, who's talking about something or other and distracting you, or you and Ricky are goofing off. No. So there are a lot of things that can happen during the lab that we can't control, but there are some that can. Those are the errors that we make. And that all brings us to this whole percent yield idea. The question is, how can we compare how much we would theoretically make if everything went perfectly according to plan versus what we actually made? So how can we compare the theoretical amount to the actual amount? And that's where this equation comes in right here. The percent yield equation compares the actual or the experimental yield, so that's what we got in the lab, and it compares it to the theoretical yield. That's what we made in a perfect situation. So if maximum we could have made 100 grams of something, but we only made 50 grams of something, then this reaction would tell us that we made 50% of what we predicted we could have. So there are those definitions for you. The theoretical yield assumes perfect conditions and gives a maximum amount. So we would have to use stoichiometry to solve for this amount, right? Whether that's 100 grams or 2 grams, who knows? And then the actual or experimental yield is how much we actually produced. And if we were in a lab situation, right, we could calculate how much of a product we would make. Then we would do the lab, and then we would measure how much we made with a scale or something, and then we would find that difference. So the actual or experimental yield is what we found in a lab. So let's look at mathematically how we can use this formula. So example 1 says, if stoichiometry predicts that we'll make 50 grams of a substance and we only make 32.5 grams, what is the percent yield of this reaction? So we can start by first addressing the question. We need to figure out what is the theoretical yield and what is the actual yield. So if we read carefully, it says if stoichiometry predicts that we'll make 50 grams. So anytime you see something like stoichiometry, or you have to use stoichiometry to come up with a number, that is the theoretical amount. And then it says we only make 32.5. That tells us that this is the lab-based component. This is the actual yield or the experimental yield. And then the problem asks us to calculate the percent yield. So all we have to do is plug in these numbers to the equation. percent yield equals the actual yield over the theoretical yield, I'm just going to abbreviate, times 100. And multiplying by 100 right there, that's how we get from a decimal to a percentage. If you remember math class, if you've got 0.5, you multiply by 100, that's 50%, just as an example. So that multiplying by 100 is the turning it into a percent. So you do not have to add an extra step to turn your answer into a percent. That's already in the equation. So then we just plug in the numbers. 32.5 is the actual yield. Make sure that you include units. And 50 grams is the theoretical yield. So I'm going to divide those numbers, 32.5 divided by 50, and then I'm going to multiply by 100. So 32.5 divided by 50 times 100, that is 65% yield. Now you might be wondering, is that good? Like, obviously we want to make 100% if possible. But realistically, due to the errors that I described earlier, it's very unlikely that we would ever make 100% of a product. Granted, there are some reactions where it's easier to get a high percent yield, and some reactions have a lower percent yield. It just depends on the reaction. But 65% I think is fairly reasonable. Something really ridiculous like 10%, it would have to have been a huge human error to get a percentage something like 10%. I would say anything in the range of 50 to 80% is fairly normal for percent yield. And you'll notice that the grams canceled out. That's because percentages can't have units. So you need to make sure that you're in the same, you have to compare same units for yield. You cannot compare grams and liters. Those don't correlate. You need to make sure that you're in the same units so that they cancel out and you end up with a perfect percentage here. Let's look at another example. Consider the reaction below, and then there's the equation there. If I start with 60.5 grams of calcium hydroxide and an excess of hydrochloric acid, what's my percent yield if after the experiment I end up actually, aka experimentally, making 14.2 grams of water? Okay, let's break this down. I've got a lot of information here. It says that I'm starting with 60.5 grams of calcium hydroxide. So 60.5 grams of the calcium hydroxide. It says I have excess hydrochloric acid. Now this goes back to something that we learned about last week, the difference between limiting reactant and excess reactant. If we have excess of something, it means that not all of it will be used. We'll have some left over. What that tells me is that if the hydrochloric acid is the excess reactant, then the calcium hydroxide must be the reactant that limits my reaction, that limits how much product I can make. So this is my limiting reactant. This is going to tell me theoretically how much product I could make. Then the question says, what is my percent yield if after the experiment I end up actually making 14.2 grams of water? So I end up actually making, so this is my actual yield. So I'm going to come back to this. The question is, what is the theoretical yield? Now remember, I said that you have to compare, apples to apples. If I actually made 14.2 grams of water, I need to know theoretically how much water I could have produced. If you notice, that 60.5 grams is of calcium hydroxide, not water. So I'm going to have to do some stoichiometry to figure out how much water could be made by this 60.5 grams of calcium hydroxide. So that's where I have to go first. First I need to use my stoichiometry skills to convert 60.5 grams of calcium hydroxide into grams of water. This is a grams of A to grams of B conversion. So if you're looking at your stoich map, I need to go from grams to moles, then moles to moles, then moles to grams. So let's set up that skeleton here. Remember, anytime you have to change substances, so going from calcium hydroxide to water, I'm changing substances, you need to use a molar ratio. And as the name implies, you cannot use a molar ratio without being in moles. So I need to convert this grams of calcium hydroxide into moles of calcium hydroxide. And then we're going to come back to that, right? We're just going to do the skeleton for now. Once I'm in moles of calcium hydroxide, I can now convert that to moles of water. This is where my molar ratio comes in. So moles of calcium hydroxide goes on the bottom, and moles of water goes on top. Remember, I know that I need to end up in water because the problem told me that my experimental yield was dealing with water. So my theoretical yield needs to match that. Once I'm in moles of water, I can convert 2 grams of water, so moles of water on the bottom, grams of water on the top, and ultimately all of my units would cancel out and I would end up with that nice grams of water. But I need to fill in all of my conversion factors first. Anytime that we have molar mass, so that would be grams and moles, we know that a 1 goes by moles. We would just need to calculate grams or the molar mass. Using the periodic table, you can calculate the molar mass of calcium hydroxide. It comes out to be 74.1. Right, so that's my first conversion factor. Then the second conversion factor, that's a mole-mole conversion. So I need to use the coefficients from the balanced chemical equation, which says that there's 2 moles of water produced for every 1 mole of calcium hydroxide produced. Then I need, in the final conversion factor, I've got grams and moles again. So I've got molar mass, and the molar mass of water is 18.02. Now I just need to calculate all of this out. So we multiply across the top and divide by everything that's on the bottom, and you come up with 29.4 grams of water, and that's how much water can theoretically be produced. This is my theoretical yield. Remember, theoretical yield is anything found by the stoichiometry. Then, once you know the theoretical yield, we can compare it to the actual yield, calculate our percent yield, simply using the equation. Percent yield is actual over theoretical times 100%. So the actual yield, 14.2 grams of water. The theoretical yield is what we just calculated, 29.4 grams of water. So if you divide that out and then multiply by 100, you get 48.3%, which is a little bit low. I'm not gonna lower than 50%, probably some errors in the experiment setup that you would need to address if you wanted to actually produce, a lot of the product. So yeah, that's how you would use our stoichiometry to calculate the theoretical yield. This reaction says 35.0 grams of hydrochloric acid reacts with 25.0 grams of calcium metal, forming H2 and CaCl2. So I'm not even going to go any farther. I'm going to go ahead and just write this reaction down. It says HCl reacts with calcium metal to make H2 and CaCl2, calcium chloride. This is a single replacement reaction. The hydrogen and the calcium switch places. I need to balance this though. And this one's fairly straightforward to balance. You just need to put a 2 in front of the hydrochloric acid. Because if you notice on the right, I have 2 hydrogens and 2 chlorines. So simply by putting a 2 in front of the hydrochloric acid, my equation is balanced. So now I've got the reaction that I'm dealing with. Let's go back and reread the problem. It says 35 grams of hydrochloric acid react with 25 grams of calcium metal. And it says how many grams of calcium chloride will be formed. Follow-up, if I only end up making 42.3 grams of calcium chloride, what's my percent yield? So again, we need to sort of annotate this question, figure out what is the information that I have. I've got two starting values. I've got 35.0 grams of hydrochloric acid and 25.0 grams of calcium. So 35.0 grams and 25.0 grams. Anytime that you see multiple masses or multiple values for your starting materials, for your reactants, that should be a pretty big hint that we are going to have to figure out which one of those, either the hydrochloric acid or the calcium, is the limiting reactant. We're going to have to figure that out, and then that number, whatever we make, that's going to end up being our theoretical yield amount, right? We're going to try to figure out how many grams of calcium chloride will be formed. So this is just like the limiting reactant problems that you guys worked on last week. I want to know how many grams of calcium chloride can I make. So I'm going to have to compare these two numbers, doing limiting reactant calculations. Then the problem says, follow up. If I only end up making 42.3 grams of calcium chloride, what's my percent yield? So we know there's a part 2 to this problem, calculating percent yield, and this 42.3 is the actual yield. So through my limiting reactant calculations over here, I'm going to have to find the theoretical yield. So let's start with that. 35.0 grams of HCl, and we want to convert that into grams of calcium chloride. So I need to set up my conversion factor. Again, this is a grams of A to grams of B. So I'm going to go grams to moles, moles to moles, and then moles to grams. That's my setup. Grams of hydrochloric acid, moles of hydrochloric acid, and then moles of HCl, moles of CaCl2, and then from moles of CaCl2 into grams of CaCl2. That'll get me to where I need to be. So again, I need to just fill in some of this information. Starting with the molar mass of hydrochloric acid is 36.46. All right, and then the second conversion factor, that's my mole ratio. For every 2 moles of HCl, I have 1 mole of CaCl2. And then I need to calculate the molar mass of calcium chloride, which is 110.98. If you cannot read any of these numbers, I apologize. Just go ahead and calculate it on your own in your own calculator. It's very challenging to write on my screen like this. So now I've got everything all set up. I just need to calculate this out, multiply across the top, divide by anything that's in the bottom. You end up with 53.3 grams of calcium chloride can be formed from 35.0 grams of hydrochloric acid. That's just part A, right? I have 2 reactants that I needed to sort out here. Now let's do the calculation with the calcium metal. So with the calcium metal, I had started with 25.0 grams of calcium. Again, I need to convert that into grams of CaCl2 because I'm trying to calculate, that's what the question asks, how many grams of CaCl2 will be formed. So this is my limiting reactant calculation, part 2. I need to do my molar mass, and I'm just going to throw this out there as we go. So if you are not with me, please go back to the mole and stoic conversions videos. 40.08 grams of calcium. And then I have 1 mole of calcium in every 1 mole of CaCl2. And this is the same as in the above reaction. So that's my setup. I just need to do a calculation, multiply across the top, divide by anything in the bottom, and I get 69.2 is my answer. That's how many grams of calcium chloride could be produced from 25 grams of calcium. Now, what this tells me is since 53.3 is smaller than 69.2, the hydrochloric acid is the limiting reactant. So this is how much calcium chloride I can theoretically produce based on the limiting reactant in this problem. I can maximum amount produce 53.3 grams of calcium chloride. Once I know that, I can go back to the question and now calculate percent yield. So remember, percent yield is the actual amount divided by the theoretical amount times 100, 102%. The actual amount is from the question, 42.3 grams of CaCl2. The theoretical amount is what I just calculated from my limiting reactant question. So that's 53.3 grams. And then we divide that and multiply by 100%. And we end up with a 79.4% yield, which I think is fairly good. Almost 80% yield is good, especially for a high school lab. And that's pretty much all I have to tell you. The only skill that we're adding into this week is percent yield, and it's just an equation. So you literally just have to plug the numbers into it. It does become a little bit more challenging since you might have to figure out that you need to do a limiting reactant calculation. And I think that comes with practice. So if you haven't done the limiting reactant videos or worksheets or even the stoichiometry stuff, you're gonna need to do that before you can do any of this. The only tip I have for you for limiting reactant is going back to this part here. If the problem gives you two starting values, you probably need to do a comparison limiting reactant calculation, okay? So let's just do a couple problems that you try on your own. I think I gave you the reactions for both of them. So it says, using the reaction below, answer the question. If I begin with 7.02 grams of Cl2 with excess HGO, what is my percent yield if I end up making 3.9 grams of Cl2O? My recommendation is to annotate this problem and pause the video, see if you can do it. I'm not going to probably talk through this one. I'm just going to put the answer up and then maybe explain it a little bit. So please pause the video. I highly encourage you to try this on your own. You totally can do it. Pause the video and then we'll be right back. Okay, so this problem had two parts. The first part was figuring out that you needed to calculate the theoretical yield. And I knew that I had to find the theoretical yield because the problem gave me 7.02 grams of chlorine, but then asked me about the percent yield of Cl2O. So I knew that I had to convert that grams of chlorine to grams of dichlorine oxide. So that was the first step, was doing that calculation to find the theoretical yield. Once I had the theoretical yield, the actual yield was in the problem, so then all I had to do was plug into my percent yield equation, and I came up with 90.7, which is a really good percent yield. So if you got that, awesome. If you didn't, please take a close look at my calculations here, compare them to yours, and see what mistakes you may have made. If you have no idea what's going on, before continuing to the next problem, you need to rewind this video and go watch the first part again. It is so to your benefit that these are video lectures and you can rewind them, because in class, you can't rewind a video, like you can't rewind my lectures. You have the opportunity to listen to everything again. So if you didn't understand it the first time, which is totally reasonable, watch it again, okay? Then come back, try these problems. Otherwise, we are going to move on to this last problem here. It says, what is the maximum amount of cesium oxide that can be produced if 81.4 grams of cesium and 7.6 grams of oxygen are reacted together? Then if we actually made 75 grams of cesium oxide in the lab, what is the percent yield of the experiment? Then it gives you the reaction and a hint. The hint says, first find the limiting reactant, then calculate the percent yield. So pause the video, do that, and then come back here for the answers. All right, welcome back. So as the hint said, we first needed to find the limiting reactant. I gave this to you as a hint, but again, you could have figured that out from the problem because the problem gave you two amounts for your reactants. So you should have known that you had to calculate which would be the limiting reactant. But when we find that O2 is the limiting reactant because it would produce less cesium oxide, then this amount, this 130 grams, becomes the theoretical yield. That's the maximum amount of CS2O that we could produce with the given reactants. Then it's just a matter of using the percent yield calculation. The 75 grams is in the problem. I calculated the 130, and ultimately it gives me a yield of 58%. Now again, if there is something that you missed here, please try again, compare your work to the work shown here on your screen. If there is a huge lack of understanding, I really hope to see you on the Zoom on Wednesday, or please email me with questions. But that's really this whole video. Again, it's just a short topic, just learning about percent yield. If you don't understand limiting reactant or stoichiometry, then we need to go back a couple of weeks to when we learned about those topics. That's it. I will see you next time, guys.